So the usual scenario we're talking about is just some container with gas inside. And what we typically care about is the pressure and the volume. In fact, we're going to be making a graph of the volume versus the pressure and keeping track of how those change as time passes. So at any given instant in time, this gas has a pressure and a volume. So let's say we've got some initial pressure and some initial volume. Then the state of the gas right now, that pressure and that volume, are represented by just a single point on the graph. And the pressure and volume in this case are examples of what we would call state functions. A state function is just any quantity, any measurement you can take that has a value at a single instant in time, a value at each instant in time. For example, we can say right now the pressure is 50 kilopascals. Or we can say 10 seconds into the experiment, the volume was 3 liters. What are some other measurements you could take on a gas or whatever at a single instant in time? What are some other measurements you could take on a gas or ways you could describe how the gas is? Yeah, temperature is another good example. You could measure the temperature of the gas at any time. And these 3 state functions in particular are, for a gas, related by what equation?
Ideal gas law?
Yeah, if we go back to the ideal gas law, which you may have seen before in chemistry, pressure times volume equals number of moles times ideal gas constant times temperature. Which means even though temperature isn't directly shown on this graph, if you know the pressure and the volume, and of course how much of the gas there is, you can figure out the temperature. So temperature can be calculated from this information even if it's not directly shown on the graph. What are some other properties you could calculate? Like for instance, if you know the temperature of the gas, what else could you figure out about it?
The internal energy of the gas?
Yeah, the internal energy. So energy also counts as a state function. The thermal energy and also the bond energy, any type of energy associated with this gas counts as a state function. How much energy the gas has right now. So these are all state functions, basically anything you can measure at a certain instant in time. Like we could say at 3 o'clock p.m., the gas's temperature was 50 degrees Celsius. Or we could say 20 seconds later, at that instant, the energy of the thermal energy of the gas is 100 joules or something. The fact that you can assign a value of each of these at each instant in time is why we call these state functions. And you could think of that function as meaning basically the same idea as function in mathematics. A function takes an input and gives you only one output for that input. In this case, you could think of the input as time. At each instant in time, you get one value for energy. At each instant in time, you get one value for temperature. So if you think of this as a function and the input is time and the output is whatever the temperature is at that time, or whatever measurement you're taking, it is technically a function. However, there are a few things that are not counting as functions, specifically what we call processes. A process instead of having a value at an instant in time, a process takes place over a period of time. And usually that's something you do to the gas over a period of time, or something done by the gas over a period of time. So what would be an example of that? What could you do to the gas over some period of time? Like, let's say you wanted to change some of these state functions. Maybe you want to make the gas expand, or maybe you want to make it a hotter temperature. Yeah, heat and work are what you could do here. You could apply heat by generally just by exposing the gas to something at a different temperature. Or you could do work by applying a force to it as it moves some distance. So heat and work can change the state functions, but heat and work do not count as state functions. Because heat and work aren't something the gas has at an instant in time. Heat and work are processes done to the gas or done by the gas over a period of time. You can't say at this instant in time the gas has 50 joules of heat. You could say over the course of these 30 seconds, the gas loses 20 joules of heat or something, but it's happening over a period of time, not existing at an instant in time. Heat and work aren't something the gas has. They're things being done to the gas or done by the gas. And they usually have the effect of changing one or more of the state functions. If you're doing heat or work to the gas, you're probably changing the pressure or the volume or the temperature or the energy, or maybe several or maybe even all of them. Presumably you're going to be changing these states to a different state. Maybe you expand the volume and lower the pressure. Maybe you change to this new final volume and this final pressure. So each of these points would represent a state. We've got the initial state of the gas. We've got the final state of the gas. But it's also going through a bunch of points in between. It doesn't just teleport from this pressure and volume to this pressure and volume. It's going to follow a path, not necessarily a straight line. This path, maybe it is a straight line. This path would be a process. And of course, each point on that path is a state that happens between those times. But the path itself would count as a process. Of course, it's not the only process. You could instead go on, let's say, maybe you just change only the volume first, and then change the pressure. So this would also count as a process, taking you from this initial state to this final state. You might be changing the pressure and volume steadily, or maybe you change the volume while keeping the pressure constant, and then drop the pressure while keeping the volume constant. Or any other combination. It doesn't even have to be a straight line. You could go on any path, just some path with direction associated with it. This would also be a process taking you from that same initial state to that same final state. So there may be many different processes, many different possible processes that could take you from this initial state to this final state. They're all experiencing the same change in pressure, the same change in volume, the same change in temperature, and even the same change in energy, because they're all starting at the same initial and ending at the same final. And how do you calculate delta anything? If you just want to calculate delta energy or delta temperature or delta volume or delta pressure, delta anything is calculated with?
Final minus initial?
Yeah, final minus initial. So all you need to know for delta any state function, all you need to know is the initial and final values. These processes are going to involve different amounts of heat and work, but they're all going to be associated with the same delta any state function. And how are heat and work related to these state functions? Do we have an equation relating those together?
I know like delta U is Q plus W, right?
Yeah, this is really all about that total energy, which we usually call energy U here. U here represents the internal energy. Internal energy is basically all of the energies contained within the object. So thermal energy, bond energy, also chemical energy, nuclear energy, maybe some others. But we usually only care about the ones that are actually changing, which is usually just going to be thermal energy. Is delta P considered a state function? Pressure is considered a state function, and delta pressure is just final pressure minus initial pressure. So those final and initial pressures would be state functions. The processes would be the things that are causing it to change, but pressure itself is a state function. And delta pressure, if you want to find the change in pressure, do you need to know which path you're taking in order to calculate how much the pressure is changing? You don't necessarily need the process. You don't need to know which path. You just need to know the initial point and final point. So generally, anything you can figure out just by knowing the initial state and final state without knowing anything about what happens in between, anything you can figure out just from the initial and final state counts as state functions. Any quantities that do need to know what process you're going through or what path you're taking, those would count as processes. Any other questions on that so far? So if we go back to the core idea of conservation of energy, that change in energy equals heat plus work. In this context, we're going to be usually calling this the first law of thermodynamics. It's the same conservation of energy we've been talking about all quarter. But in this context, we call this the first law of thermodynamics, the study of heat flow and temperature and stuff like that. First law of thermodynamics, conservation of energy. And we're usually going to write this as delta U. It still means energy. We're just specifically talking about internal energy, the energy contained within this gas. And looking at that in more detail, internal energy is just all the energy contained within the object. So that includes thermal energy, that includes bond energy, and chemical energy, and nuclear energy, the energy contained within the atoms themselves, all these types of energy. But usually we don't care how much energy there is, we just care how much it's changing. So if we apply a delta to all of these, if you just got this gas in a container, is this gas experiencing any nuclear fission or fusion? No. So maybe it has nuclear energy, but the change in nuclear energy is 0. It's not experiencing any chemical reactions. So it has chemical energy, but the change in chemical energy is 0. And likewise, bond energy only changes under what circumstances? Yeah, a phase change. We're assuming no phase change here. We're assuming it's a gas the whole time. So change in bond energy would also be 0. The gas might be changing temperature though, so we should expect possibly a delta E thermal. That means for our practical purposes, delta U is just delta E thermal. And of course, if there's a phase change, we would also include delta E bond. If there's a chemical reaction, we'd also include delta E chemical. If there's nuclear reactions going on, we'd also include delta E nuclear. But for our practical purposes, just a gas in a container that stays a gas, we can assume delta U is synonymous with delta E thermal. So the change in thermal energy is heat plus work. Any questions on that so far? So delta any state function, delta U, this side of the equation you can find just from initial and final values. You don't need to know what's happening in between. This side of the equation is what's happening in between. The heat and work are dependent on which process you take. So if you consider these 3 different processes we've marked on the graph, each of these 3 processes has the same delta U because they all start at the same initial state, they all end at the same final state. But they're going to have different amounts of heat and work because they're taking different paths. The heat and work have to add up to the same delta U. They're just going to be split up differently. Like let's say we calculate delta thermal energy and we find that it's 500 joules. Maybe one path might be 200 joules of heat plus 300 joules of work. Another one might be maybe 500 joules of heat plus no work at all, or no heat at all, but 500 joules of work. Or maybe it's split up with some negatives also. Maybe, for instance, 700 joules of heat plus negative 200 joules of work. Those still add up to 500 joules. So there's infinitely many possible combinations that would add up to the same delta energy. And what would a negative mean here? Why would we distinguish between positive amounts of heat or work versus negative amounts of heat or work? What's the difference between positive and negative? Yeah, leaving versus entering. In general, the convention we're going to use is heat and work, both heat and work are positive if they're entering the gas and negative if they're leaving the gas. So positive values for heat and work and delta energy mean energy entering the gas. Negative values means energy leaving the gas. And how would you calculate the heat, or is it given? Heat is usually the most difficult to find on a graph like this. Energy you can find just using the initial and final values. Work, it turns out, you can find using the process, the path itself. So usually you would find delta U from the initial and final values, figure out work from the path, and then you could just subtract to find heat. Or alternatively, maybe the heat is given. Maybe we know the heat, and then we can use that to figure out something else about delta U or the work. But typically you're going to be finding some of this information from the graph, and or maybe some of it is given. And this first law of thermodynamics, sometimes combined with the ideal gas law, ties all of that together. So as long as you can set up these equations and get some of the information from the graph or other given information, you can then solve for the missing information algebraically. It's largely just a question of making sure that's all well organized and knowing what information to use where and how it all fits together. And how to interpret the graph, of course. Any other questions on that so far? Then let's take a look at a few specific types of processes. Because like I said, there's infinitely many different processes that could take you from initial state to final state. But there are some specific types of processes that become very predictable. And these are the ISO stuff, isothermal, isobaric, isochoric, that somebody was mentioning earlier. One example, let's say we're looking at let's say isochoric for now. What would isochoric mean? What's the interpretation of that? Where have you seen the root word iso before?
Iso means constant, right?
Yeah, constant or same or equal. Yeah, isotope. Isotope. I forget exactly what tope means, but iso in the isotope just means it's the same type or different variations on the same type of element. Also showing up in geometry, isosceles. What does isosceles mean?
Equal-sided triangle.
Yeah, you've got two of the sides being the same. Scalous, if I remember correctly, is just Greek for leg. So isosceles is a triangle whose two legs are the same. And this is going to be the same thing in all of these terms. Iso just means same or equal or constant. It's not changing during this process. And choric specifically is referring to space, how much space something takes up. So isochoric just means constant volume. It's the same amount of space all the time. A process in which volume does not change. Delta V equals 0. And delta V being 0 just means we start and end at the same volume. This is actually a slightly stronger statement. We're saying the volume does not change during the entire process. So if we were to draw that out on a pressure volume graph, if we're assuming the volume does not change, what would that process look like? Yeah, it's going to be a vertical line. No change in volume means we can't move left or right at all. We're not moving along the volume direction at all. So we've got some initial state and some final state. It actually could be going in either direction. Let's say we're going from a high pressure to a low pressure. So this would be an example of an isochoric process. It's got an initial pressure, Pi, a final pressure, Pf, but it's only got one volume, let's say V sub 0. And it just stays at that volume the whole time. And let's investigate what this would actually look like. If you've got a container with a gas in it, let's say you've got this gas, We want to put this in, we want to build a container or design an experiment that makes absolutely certain that the volume does not change. How could you set up a chamber to put this gas in that does not allow the volume to change?
Have it be closed?
Yeah, it's got to be closed. Certainly closed. I mean, technically these all need to be closed because we don't want any gas entering or leaving. But specifically, we want it to be closed in such a way that the walls do not move. We want this closed, rigid-walled container so that no matter what happens to the gas, the walls don't move, so the gas can't expand or contract. The gas is always taking up the same amount of space. So a convenient way to set up an isochoric experiment is to just put it in a rigid-walled container. This sealed box with completely rigid sides that cannot expand or contract. Alternatively, let's say you did want the volume to change. If you wanted to set up a container that allowed the gas's volume to change, how would you allow that? How would you allow the gas to expand and contract? What could you build into the container that would allow the gas to expand and contract? Either non-rigid walls, like maybe you allow the walls to bulge out or flex in. If you have flexible walls, or maybe like a balloon or something, that would allow the volume to change. But the problem is that that is going to be a very uncontrolled sort of way. If the walls can flex, then you can't really control that in a very predictable way. How could you build a wall that moves exactly in the way you want it to? Like, let's say we just make these walls and floor fixed in place, but we allow the ceiling to rise up on tracks or go down on tracks. What do we usually call that if one of the sides is movable? So we can push that in to squeeze the gas or stretch it out. If we've got a container, but one of the walls is flexible, not flexible, but movable, and maybe has a handle. Yeah, a piston. So typically, if you do want the gas to be able to expand and contract, you build a container with a piston. And then if you want the gas to compress, you can just push in on the piston. If you want the gas to expand, you can pull out on the piston. And if you don't want the gas to expand or contract, if you want constant volume, you can still do it with this. You just lock the piston in place. So an isochoric process could be interpreted as a sealed, rigid-walled container, or a sealed container with a piston, but you've locked the piston in place. Either way, we want a situation where the gas cannot expand or contract. The walls of the container do not move at all. So what does that tell you about the values in the first law of thermodynamics? If nothing moves, if the walls of the container cannot move, what does that tell you about these values? Yeah, work equals 0. Because work, if we think of this as our usual force times distance, the gas is exerting forces on the walls of the container. This is really what pressure is all about. Pressure is talking about, technically pressure is force over area. This is the definition of pressure. Pressure, if the gas has pressure, that just means that the gas and the walls are exerting forces on each other. The amount of pressure is force divided by area, how concentrated the force is. So lots of pressure means lots of force in a small amount of area. It's very concentrated. A small amount of pressure means the force is more spread out over a wider area. A little bit of force over a large area. But the very fact that the gas has pressure means there is force involved. But why doesn't that force count as doing any work? Like if I'm pushing on the wall here, I'm exerting a force on the wall. Why doesn't that force count as doing work? Yeah, it's not doing the force over a distance. There's no motion involved. Even though the gas is exerting a force on the walls, the fact that the walls are not moving means that this force does not also count as work. So walls do not move, and therefore work is 0. There is no work being done here. The walls are not doing work to the gas is not doing work to the walls. So going back to our first law of thermodynamics, we can replace W with 0. So delta U is just Q. In other words, if you're in an isochoric system and you want to change the energy of the gas, the only way you can do that is by adding or removing heat. Is that possible? If you got this gas in a rigid wall container, how would you add or remove heat? What causes heat to flow in the first place? Like, why would heat flow from one place to another?
Couldn't you just heat the container?
Well, what does that mean? How do you apply heat to a container?
It'll be next to a hotter thing.
Yeah, if you just put this container in contact or nearby something that's at a higher temperature than the gas, heat is naturally going to flow from hot to cold, from high temperature zone to low temperature zone. So to cause heat to flow, all you need to do is put this gas in contact with something that's at a higher or lower temperature. If you want heat to flow into the gas, just put it in contact with something hotter, maybe put it over a flame or something. Or if you want heat to leave the gas, just put it in contact with something colder. Maybe take this container and dunk it in an ice bath or something. So it's definitely possible to cause heat to flow. Note that we're not assuming any insulation here. We're assuming that these are rigid walls, they can't move, but they're not insulated. We're assuming they allow heat to pass through easily. So heat can definitely flow, which causes the internal energy to change. And specifically, what type of energy are we considering here? Yeah, it's thermal energy. So what's really going on here is you're putting the gas in contact with something at a different temperature, and as a result, the gas's own temperature changes as energy enters or leaves. And this also ties in with the ideal gas law. If we apply a delta to both sides of this, we're assuming volume is constant. If volume is constant, what can you do to a constant multiplier inside a delta?
Take it out?
Yeah, constant multiplier can be pulled out of the delta because delta just means final minus initial. So that would be pressure final times the volume minus pressure initial times the same volume. Since it's the same volume, we can factor that out and just get volume times delta pressure. Likewise, what's the only thing changing on the right side?
Temperature.
So that means N and R are constants and can be pulled out. So we just get NR times delta T. So the change in pressure is directly proportional to the change in temperature. Change in pressure equals a constant times change in temperature. In this particular graph, what's happening to pressure? If we're going from this initial to this final, yeah, pressure is decreasing, so delta pressure is a negative change, which means temperature has to be changing in the negative direction also. This decrease in pressure combined with no change in volume corresponds to a decrease in temperature as well. This represents a gas that's getting colder and thus losing pressure, even though it's staying the same volume. And we can even see that directly from just PV equals nRT. Decrease the pressure while keeping the volume the same, and the temperature has to decrease to balance that out. So this would represent making a gas colder and therefore decreasing the pressure, presumably by removing heat from it. We could even figure out how much heat. If we just calculate change in energy, that's going to be the same as the amount of heat. And we can calculate change in energy using some of the formulas we've already seen. We already saw, for instance, going back to our microscopic version of the formula for thermal energy, using the idea of number of modes, the final equation we got to there that I think is going to be most useful here is the N times R times delta T times number of modes over 2 as a formula for change in thermal energy. So we could find the delta temperature by using the ideal gas equation. Or more conveniently, what could NR delta T be replaced by? Yeah, nRT equals PV. And note that here we don't have nRT, we have nR delta T. But if we apply a delta to both sides, we would get delta PV. In this particular case, volume is constant, but more generally, it doesn't have to be. So I would replace nR delta T with delta PV in parentheses, in the sense that we'd be taking final pressure times final volume minus initial pressure times initial volume, times number of modes over 2, equals delta E thermal, which in this context, we're just going to call delta U. So this is a very convenient formula for the delta energy in the ideal gas, or in the first law of thermodynamics, that we can calculate delta U from the graph, because we can look up the pressure and volume changes on the graph. So from these data points, initial and final values, just calculate final pressure times final volume minus initial pressure times initial volume. Multiply that by number of modes over 2, and that's the delta U in the first law of thermodynamics. If you know the work is 0, then that delta U is equal to the heat. Any questions on that so far? And presumably in a graph like this, these values would probably be labeled. You probably know the initial pressure, final pressure, and the volume as numbers. You could fill those into this formula. And if you know the number of modes, then you can calculate the delta U, and that's going to be equal to the heat because there's no work done. Or alternatively, maybe the heat is given, and then you could solve for number of modes, and that gives you some information about what type of gas it is. Any other questions on that so far? So I think those are the main things to know about an isochoric process. Isochoric process, no change in volume means work is 0. So we get this specialized first law of thermodynamics. The new first law is just delta U equals Q, because there is no work. And that's going to look like a vertical line on the graph. We can treat that as a gas in a rigid walled container, or with a piston, but the piston locked in place. Any questions on the isochoric process so far? Then let's try applying the same approach to an isobaric process with constant pressure. In an isobaric process, we're assuming the pressure does not change. No change in pressure throughout the entire process. So on the graph, what would that look like?
Horizontal?
Yeah, it'd be a horizontal line, because we'd have one single pressure, let's say P0, that doesn't change, but we'd have the volume either increasing or decreasing. Let's say we've got an increase in volume here. We're going from a small initial volume expanding to a larger final volume. So our process would look like this then. And again, let's take a look at what would cause that. In this case, the volume is allowed to change. So we should assume we're in a container with a piston. The piston is free to move up and down. We've got this gas inside the container. We're allowing the volume to change, but we're assuming the pressure has to be constant. And if pressure equals force times area, or force over area, the only thing we can really control here directly is the piston, because the walls, these other walls we're assuming are fixed in place, but the piston is free to move. If we want a constant amount of pressure, we could look at the force exerted on the piston divided by the area of the piston. Is the piston's area changing? Like if this piston is able to move up and down, would you expect its cross-sectional area to change? Is the piston itself expanding or contracting?
No, not on the piston.
Right, the piston's not going to be changing area. The piston's going to change height. It could go up or down. But the piston itself is just this, maybe this metal plate or a plastic plate or something. It's not like the piston is getting smaller or bigger. The piston is just moving forward and backward. So the piston's area does not change. The area of the piston is constant. And we want the pressure to be constant because we want this to be an isobaric process. So what's our requirement then? If we want the pressure to be constant and the piston, of course, can't change its area, what does that tell us about the force?
The force has to change, or actually it can't change.
And we want the result to be constant. So we've got to make sure the force does not change. The force must be constant as well. Specifically, the force applied to the piston. So the only way for this to work, the only way to make this gas in a piston isobaric is to make sure that the piston's exerting a constant amount of force. You can't like push harder on the piston sometimes or weaker sometimes. You can't push sometimes and pull sometimes. You got to have a constant amount of force on the piston. And one very convenient way to do this, what's a force we already know of that doesn't change? Very simple, naturally occurring force, does not change at all.
Gravity?
Gravity. The simplest way to set this up experimentally is to just put some weights on top of this. Just stack some rocks or metal blocks or something on top of it and just leave it there. Don't touch it. So this weight exerts a constant force of gravity on the piston. And this is actually why we call it isobaric. Baric means having to do with weight. Isobaric literally means constant weight. So this is just a constant amount of weight pushing on the gas. That makes sure the pressure does not change. Any questions?
But wouldn't the further you push down, doesn't that, like, I feel like intuitively makes the gas more concentrated, right?
Yes, it would make the gas more concentrated. But let's compare that to the ideal gas law. Because let's say we do want the gas to, let's say we want the gas to shrink. We want the weight to go down. You can't push harder on it because that would change the pressure. You have to keep the same push on it. So we got the pressure must be constant if we're assuming this is isobaric. But let's say we want the gas to shrink. So we want volume to decrease. If the pressure must stay constant because it's an isobaric system, but we want the volume to decrease, what else has to happen to make that work? If pressure is constant, but the volume is decreasing, what else has to be happening?
Something happening to the temperature. It's also decreased.
Right, the temperature must decrease. So in an isobaric system, like if you didn't care about it being isobaric, you could change the volume just by pushing harder on the piston. That's going to increase the pressure, but decrease the volume. But if we want the pressure to stay the same and we want the volume to decrease, the only way for that to work is for the temperature to decrease. So the way you would make this piston get lower and lower and lower is by dropping the temperature of the gas. Making the gas colder allows it to condense into a smaller space, even though it's staying at the same pressure. And how would you do that? How would you make this gas get colder?
The same way we did the other one, right?
You just remove some heat. You put it in contact with an object colder than itself. Maybe dip the whole thing into an ice bath or something, a vat of icy water. That's going to cause heat to leave the gas. As the gas loses heat, it's going to get colder. Temperature decreasing causes the volume to decrease proportionally. So it's going to shrink into a smaller and smaller space, allowing the piston to descend. Or conversely, if you want to expand the gas, just put it in contact with something hotter than itself. Maybe you put this over a burner or something. As heat flows in, then temperature increases, pressure stays constant because it's a constant amount of weight. So the volume is going to increase to balance the temperature increase. As the volume expands, this lifts the piston up. So that takes care of the heat in the first law of thermodynamics. Is there a possibility of any work being done? There should be a possibility of work done, right? Because we're still defining work as force times distance. The piston is exerting a force on the gas, a constant amount of force. Is the piston able to move? Yeah, piston can move up and down. And note that it can only do so if we're changing the temperature. So it's not so much that we're deliberately doing work here. It's not like you're doing work by reaching in and pushing the piston further down or pulling it further up. You're not really deliberately doing work here. You're deliberately adding and removing heat. But the adding or removing heat causes the temperature to change, which causes the volume to expand or contract, which causes the piston to move, and that moving piston counts as work. Even if it's not a deliberate effort on the part of the experimenter, the fact that the piston is moving means that there's a force being applied as something moves, and that counts as work. So work is being done as the piston moves. And you can also kind of see this in terms of conservation of energy. Like let's say you add some heat, the gas expands, the piston rises up. That means you've got a heavy object that's moving upwards. What type of energy is usually associated with a heavy object moving up or down? Yeah, potential energy, specifically gravitational potential energy. I wouldn't say it's spring potential energy here because it's not like we're attaching a spring to the piston. You could attach a spring to a piston, but the problem is that would be a changing amount of force. As the spring gets more or less compressed, the force changes. So that would not be isochoric or isobaric. It would be a very different scenario. The pressure would be changing over time. But with the weight attached, it would be gravitational potential energy. Let's say you add some heat to cause the gas to expand. What's happening to the potential energy of gravity of the piston? If you're expanding the gas, what happens to the potential energy of the piston? Yeah, that potential energy is increasing. And that potential energy has to come from somewhere. Specifically, it comes from the gas doing work to the piston. So if the gas is expanding, then that means the gas is doing work to the piston. And that counts as work leaving the system. So if the gas is expanding, then the gas is doing work on the piston. So we would say work is leaving the system. Expansion means work is leaving. So we're going to treat that as work being a negative value. On the other hand, if the gas is compressing, if the gas is shrinking into a smaller and smaller and smaller space, what's happening to the piston? If you allow the gas to shrink. If the gas is shrinking, what happens to the potential energy of the piston? Well, the piston is going in the downwards direction though, right? Yeah, so it should be decreasing. If the gas is shrinking, that's allowing the piston to move down. So that means the piston is losing potential energy of gravity. And that means that work is being done to the gas. If the piston is losing potential energy, that energy has to go somewhere, and it specifically goes into the gas. We'd say the piston is doing work to the gas. Since work is entering the gas, we're going to treat that as a positive amount of work. And if you have trouble remembering this, imagine, and I find it helps to imagine that, like, let's say you're holding this container in your hands. To compress the gas, you have to do work to make that happen. So you're adding work to the gas. To allow the gas to expand, the gas is naturally trying to expand anyway. So you just have to relax and let the gas push your hands outwards. So that would be work leaving the gas because the gas is doing work to your hands as it pushes them outwards. So I find that's a useful way to visualize that and remember which of these is which. In this case, for instance, what's happening to the volume if the graph is drawn exactly like this? From this initial to this final, the volume is increasing, yeah. In this graph, the volume is increasing. So what does that tell you about work? I wouldn't really say work is decreasing. I would say work is causing the energy to decrease. But in terms of work, Remember, work is not a value that the gas has. Work is a process being done over a period of time. So we would describe it as, is work entering versus leaving? Yeah, I would say work is leaving the system. So we're going to say work is a negative value. But keep in mind, work is not a value that the gas has at a certain instant in time. Work is what's happening to the gas over a period of time. Since work is leaving the gas, we're going to describe that as work being a negative value. And we can even calculate how much work, again, based on the idea of force times distance. But we can make some substitutions here. We know work is force times distance. Also, pressure is defined as force over area. If you solve this for force, what do you get? Yeah, multiply both sides by area, you get pressure times area. We can now substitute that into this formula. So work equals force, which is pressure times area, times distance. If we now combine these differently, if we group together area times distance, think geometrically. If you take an area multiplied by a distance, what are you creating? Specifically, the area of the piston times the distance it travels. Area times distance, what are you tracing out there? That's volume. You can also see that in terms of units. You got meters squared times meters, that makes meters cubed. So area times distance is volume, specifically the change in volume of the gas as the piston moves. So we could write this as pressure times change in volume. Also, if the volume's increasing, we want work to be negative, and if the volume's decreasing, we want work to be positive. So we also need a negative sign here to get those signs to balance out. This is a formula that allows us to find the amount of work done in an isobaric process, at least. And take a look back at this graph. If we've got the pressure, this amount here, times the change in volume, if you multiply this distance times this distance, geometrically, what does that tell you? What do you get if you multiply height times width? Physically, that's work. On the graph, it's area. So that means that the area enclosed under the graph, from initial volume to final volume, the area enclosed under the graph is the work. Explain the negative. Yeah, the negative here is basically just to make these signs match up. In this case, for instance, the volume's increasing, the gas is expanding, so delta V will be positive. But if the gas is expanding, work is leaving, so we want work to be negative. Work and delta V have to have opposite signs. So we need this negative here to make those signs match up. You could also think of it as the direction the weight is moving. Like, let's say the weight moves forward or downwards. That's causing the gas to shrink in volume, so delta V is negative. But it's doing work to the gas, so we want work to be positive. So it's really about a directionality. But this allows us to calculate the work done for the isobaric process. This formula specifically only works for isobaric process, but the idea that work is the area under the curve is more general. For any process on a pressure volume graph, the area from the curve down to the axis is the amount of work done. Even if it's not a straight line, even if it's some weird curve, if you can find the area under the curve, that is the amount of work. And this gives us a very convenient rewrite of the first law of thermodynamics. Delta U is still heat plus work, but now that we know work is negative P delta V, we just get Q plus negative P delta V. So this is our modified first law of thermodynamics, conservation of energy, for specifically an isobaric process. If you can find the area under the curve just as P times delta V, and you can find delta U using this formula and number of modes and the pressure and volumes from the graph, then you can solve for the amount of heat. And that tells you how much heat is necessary to make this process happen. Any questions on that so far? All right, so those are the two big ones. We can take a look at some of the other processes. Isothermal and adiabatic are the other big ones, and how this applies to heat capacity next time. But in the meantime, try getting some practice on this. Just draw out some graph mark some numbers for initial pressure, initial volume, initial or final pressure, final volume, and see if you can use that graph and these equations to calculate all these values. The amount of the change in energy, the amount of heat required, the amount of work required for that process. So give that a try, review the idea area under a curve from calculus if you need to, and I will see you next time.